All right, so good morning, everybody. I hope you are enjoying the extra sunlight we're getting nowadays. It's very lovely and spring feels like it's right around the corner. Couple quick announcements before we get started. So we just completed our chapter 1 quiz last week on Friday. So now we are well into chapter 2 work. So we started with limits and continuity. We'll be doing more chapter 2 work today, but this is a regular week this week. So we have our mini quiz on Wednesday and Sunday with homework due on Sunday. And then next week it's a little goofy. Monday is a holiday. And so Tuesday follows a Monday schedule, which means that we will not see each other next week on Tuesday. So I'll send a reminder out about that near the end of this week. So for our weekly review sessions, we've been doing different topics. Last week was sine and cosine. So this week on Thursday and Monday, the review will focus on graphing the derivative, which is we're going to be working on what the derivative is today. And then on Thursday about what it looks like. So if graphing is something that you have a little bit of trouble with anyway, you may want to try to attend one of those. Or if when we go through things on Thursday, if that seems a little, like you need a little more practice, you can plan on going to those. And as always, after the review sessions have happened, the videos of those are posted under Getting Started on Moodle. So if you can't attend, but you would like to review one of the sessions, you can find the links for those there. Other than that, I think we are in good shape to just kind of keep rolling forward. So today we're going to be talking about what's called the instantaneous rate of change. And so we are going to sort of connect two big ideas that we've already covered. So we're going to take the average rate of change, which we did in 1.3, which was how much a function changes on average. And we're going to connect that to the idea of limits, which is what we looked at last time. So that's sort of our goal for today, is to start learning what it is, what it represents, how do we start approximating it, and we'll go from there. So I'm going to switch over to the DocCam. Okay. And so as a reminder, the only way we were able to talk about rates of change so far was with the average rate of change. And the way we did that is by looking at the slope of the line that connected 2 points. And so we got a formula f of b minus f of a over b minus a, which calculated the slope of that line. And that was called a secant line. A secant line is a line that connects 2 points. So we took this idea of slope, we were able to go ahead and bring it in to approximate how much a function changes between 2 points. And we did that on graphs and tables and all sorts of things back in 1.3. So today, our goal is to develop an understanding of how we might get to what's called the instantaneous rate of change. And so the instantaneous rate of change is how much a function changes at 1 point. So instead of thinking about how it changes between 2 points, we're going to say, okay, if we can figure out how much this function changes at 1 point, then we can find out for all the points, and then we'll have a better way of talking about rates of change because it won't be approximated anymore. But in order to do that, we have to first figure out how to figure out how much a function is changing at 1 point. And so the instantaneous rate of change has a lot of names, and we're going to talk about those after we learn a little bit more about it. But the idea is that we are still trying to figure out how much a function changes, right? That's sort of the big picture idea. So the way that we are going to approach this is we are going to take what we do know how to do, which is average rate of change, and see if we can use that to figure out what we don't know yet, which is the instantaneous rate of change, right? So what we're going to do, like I said, is we're going to combine this idea of average rate of change and limits to see what we can determine. Okay. Now, conceptually, what is the difference between average rate of change and instantaneous rate of change? Imagine that it takes you 3 hours to travel 150 miles to your cousin's house, right? They live 3 hours away. Your average rate of change is going to be 50 miles per hour, right? Because you went 150 miles. It took you 3 hours. So if you divide 150 divided by 3, you get 50 miles per hour. That was your rate of change on average for your trip. Your instantaneous rate of change, however, is the rate of change you are going at any moment in time. So if you look down and your speedometer says, 25 miles per hour, that is your instantaneous rate of change. That is your rate of change at that moment, right? And we know that the speedometer will go up and down. So if you look at it, whatever it says in that moment is your instantaneous rate of change, how much you're changing in that moment, okay? So let's consider that we want to try to understand approximating the instantaneous rate of change. And so what we want to do, like we said, is we want to use the average rate of change because that's what we know how to do. So what we're going to do is we're going to try to figure out how to use the average rate of change to get to the instantaneous rate of change by bringing in this idea of limits and closeness. So our goal is to think about the instantaneous rate of change at x equals -1. So that's what we're trying to think about, right? How much is our function changing at -1? So -1, we can see is right here, and this is the point that we're interested in. We want to know how much are we changing right there, okay? Well, we don't know how to do that yet. What we do know how to do is average rates of change. So our approach to this is going to be to look at the average rate of change to the left of 1 or -1 and the average rate of change to the right of -1. And so when we do this, this is very similar to when we started looking at limits and we picked something a little bit to the left and a little bit to the right to see what was happening, right? That same idea is being applied here. And so for this first visual, the amount that I picked is 1 unit, right? So from -1 to -2, that has a difference of 1. And then over here, if you look at the right-hand approximation, it's from -1 to 0. So just like when we did limits, when we use a left-hand average rate of change and a right-hand average rate of change, we want to go the same distance away from the number we're interested in. And so here, this visual is 1 unit. So how did I do this? How did I do the average rate of change? Just as a reminder. So for the left, and it's the left because the point is here, so I'm picking another point to the left. When I do the average rate of change, I'm going to do f of -1 minus f of -2 divided by -1 minus -2. Okay, so f of b minus f of a over b minus a. So f of -1, I'm going to come up here, I'm going to come over here. That's going to give me 0.5. So I have 0.5 minus, and now f of -2 means I'm going to come to the -2. I'm going to go up to where it hits the function. I'm going to come over. I see that that value is +2 divided by, now on the bottom, I'm being extra careful because I have minus a negative. So divided by 1. And this gives me my -1.5. So the slope of this secant line, which is the average rate of change to the left, is -1.5. Okay, I was expecting it to be negative because this line is downward sloping, and so I knew the slope had to be negative. Now I do the same thing to the right. Okay, I'm going to do an average rate of change to the right, again, 1 unit away. So when I do that, I have f of -0.5 minus f of -1 divided by -0.5 minus -1. Okay. Oh, wait, that's 0, 0. Let's go back. Ignore that. That was wrong. I read that completely wrong. Cross that out. We all make mistakes. Okay. So I am 1 unit away. So -1 to 0. So I was using the wrong values. So I'm going to do f of 0 minus f of -1 over 0 minus -1. Okay. So f of 0, I go to 0 and I see that that value is 0. F of -1, that's the same value I found before, which is 0.5 divided by, now on the bottom, I have 0 minus -1. So again, if you have a minus and a negative, those are going to cancel each other out. So I'm dividing by 1. So this is going to give me -0.5. So I see that the slope to the right is -0.5. And again, I was expecting it to be downward sloping from the left to the right. But what does that tell me, right? I want to know how much the function changes at this point. I know how much the function changes to the left of the point and how much it changes to the right of the point. But what kind of information does that tell me about the point? Well, it turns out that when you do the average rate of change to the left and the right, it provides bounds for where your instantaneous rate of change needs to be. So that means my instantaneous rate of change, which I'm going to write as IROC, just because I don't have a whole lot of space, has to be between the left hand approximation and the right hand approximation. Okay. So now I know that my instantaneous rate of change, the amount that I'm changing right at this point, has to be between -1.5 and -0.5. Now, how helpful is that, right? Like, that's better than what I knew before, because I didn't have any way before today's class of knowing what the instantaneous rate of change was, but it could be anywhere in here, right? So this is where we're going to use our strategies about closeness to see if I can come up with a better approximation. And so what I'd like to do is I would like to repeat this process by looking to the left and to the right of -1, but get closer. So instead of going 1 full unit away, let's go half a unit away on either side and see if that helps us figure out a better interval. Okay, so I'm going to have you try this. And the idea is that we want to look to the left and the right, and I just want you to get comfortable with setting things up. So again, -1 is what we're interested in. This is the same exact picture, same exact function. When we look to the right, this is -0.5. And then to the left, we're using -1 and -1.5. Okay, so I'm going to draw just little, I don't know what you call these little dashed lines over so you can kind of see where it hits the axis. You are going to have to do a little approximating about what you think these values are. But I want you to approximate the average rate of change to the left and to the right, just like we just did, to see what happens when we get a little bit closer. Okay, so again, the span is now 0.5, and this span is 0.5. Before it was 1. Okay, so I'm going to give you 2 minutes. See if you can set up the average rate of change on the left and the right. Try to do an approximation, and then write out what the bounds are going to be now for our instantaneous rate of change, because it'll have to be between the left and the right. Okay, so take 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so let's start with the left-hand approximation. So when we do a left-hand approximation, we are interested in looking at what's happening between -1 and -1.5. So f of -1 minus f of -1.5 divided by -1 minus -1.5. So f of -1, we come up here, we get 0.5. That's the same as before. But now for f of -1.5, we have to approximate this value here. So I'm just going to share with you how I came up with the number I approximated. Yours might not be exactly the same, but it should be roughly in the same, general area. So I tried to find the halfway point between 1.5 and 1. And so I know that halfway between 1 and 1.5, right, is going to be 1.25. And then this to me looked like it was halfway between 1 and 1.25. So that's how I did my approximation. Again, yours might be slightly different, and that's okay. But as long as it's in the same general region / idea. So I have 1.125. You might have 1.1, something like that. That's okay. Divided by, now down here, again, I'm being really careful with my negatives and my minuses, right? And so this is going to be divided by 0.5. Okay, when I crunch this number in my calculator, I get negative 1.25. So negative 1.25 is my approximation on the left, right? And again, if you use slightly different numbers, this might be slightly different, but it should be around there, okay? When I do my average rate of change on the right, I'm using 0.5 minus f of negative 1 divided by 0.5 minus negative 1. So f of 0.5, right? I'm coming up here. I'm getting this value here. Again, I did something similar to what I did up here. I found the halfway point, which is here. And I said this is 0.25. And I looked like it was about halfway between those two. So I use 0.125 minus, and then we know at negative 1, it's 0.5, all divided by 0.5. Okay, so when I crunch that number, I get negative 0.75. That's my slope. And again, I was expecting both of my slopes to be negative since these lines are downward sloping. So how does this compare to when we were further away? So before, we knew that our instantaneous rate of change had to be between negative 1.5 and negative 0.5. So that was a span of one, right? So one whole integer, I had to be on that number line somewhere in there. And now, with my new approximations, I have negative 1.25 and negative 0.75, right? So now my span of where my instantaneous rate of change has to be is 0.5. So that is a smaller interval where my instantaneous rate of change needs to be, which means it's a better approximation. Okay, so what does that tell us? That tells us that the closer we can get to negative 1 when we're doing our left and our right hand approximation, the better our bounds are going to be. We're going to get a better approximation of where the instantaneous rate of change needs to be. Okay, so what is the goal? Like, what is the ultimate goal? Well, the goal is to get this span to be as small as possible, essentially to 0. Because if we find something like the instantaneous rate of change needs to be between 5 and 5, then it has to be 5, right? Because if it's the same on the left and the right, then we have the instantaneous rate of change. So what's happening is that the slopes from the left and the right are getting closer and closer to each other as we do this. And eventually, if we get close enough, then the slopes of the lines will be the same on the left and the right. And that, when that happens, is the exact instantaneous rate of change. So if you were to keep getting closer and closer to negative 1, what would happen is eventually the left hand and the right hand average rates of change would become negative 1. And when they're both negative 1, the left and the right connect and make one line. So when that happens, you get the instantaneous rate of change. And when that happens, we get a new line that we need to define. So we call this line that touches just at one point the tangent line. Okay, so the tangent line touches at one given point, and the slope of that line is the instantaneous rate of change. So just like the slope of the secant line is the average rate of change, the slope of the tangent line is the instantaneous rate of change. So this is our goal, right? Our goal is to be able to figure out how to get the average rate of change on the left and the average rate of change on the right to become as close as possible. And we mentioned that we want to get really, really close to the number we're interested in. So in this case, if we were able to do like negative 1.01 and negative 0.99, that would probably get us pretty close to the slope of negative 1. Okay, so we're going to practice getting closer and closer in different ways, right? So we did this, we said, looked at this first on this graph, but now we're going to look at it on a table and start looking at how we get closer and closer. Okay, so let's look at this example here. And here's the scenario. Consider that I have thrown a tennis ball up into the air and I have the ability to measure the height of the ball, which we're calling S of t. You can see the heights down here in feet for time t, where time is in seconds. And I'm recording the data in the table below. So at time equals 0, the ball is 6 feet in the air. So I am 5'6", which means that if I lift my arm up to throw a ball, the minute I let go of it, it's about 6 feet in the air. Okay, so then it goes up after 1 second, it's at 9 feet. After 2 seconds, it's at 11 feet. After 3 seconds, it's 12 feet. After 4 seconds, it's back down to 10 feet, right? Because gravity, once it goes up, it's going to start coming down. So I want to know how quickly the ball is going up at time equals 1. Okay, I'm interested in the instantaneous rate of change at 1. So how fast is the ball traveling at time equals 1? That's the question I'm trying to answer. So I'm going to do an average rate of change to the left. I'm going to do an average rate of change to the right. And that's going to give me my bounds for where the instantaneous rate of change needs to be. So we've done average rates of change on tables before, but just as a reminder, we're still doing f of b minus f of a over b minus a. So what I'd like you to do is I'd like you to find the average rate of change to the left of 1, the average rate of change to the right of 1, and then set up your interval where your instantaneous rate of change needs to be. It has to be between the two values. If you have enough time and you think you can do it, add units to your numbers. We'll talk about the units when we do it together. Okay, so I'm going to give you a minute and a half, 2 minutes, but do your average rate of change on the left and the right, and then we'll talk about it together and talk about what kind of information it tells us. Okay. Okay, take about 30 more seconds. All right, so let's look at the average rate of change on the left and the right here. So when we do it on the left, we are using 1 and 0 here as our independent values. So f of 1 minus f of 0 over 1 minus 0. F of 1 is 9 minus 6 divided by 1 equals 3. So let's talk about units here. So here on the top, we have our f of 1 and our f of 0. So these are our dependent units, which are feet. And then on the bottom, we have 1 minus 0, which were our independent units, which were in seconds. So this is 3 feet per second. So the ball was changing approximately on average 3 feet per second from time 0 to time 1. We are also interested in doing the average rate of change to the right. So we're going to do f of 2 minus f of 1 over 2 minus 1. F of 2 is 11. F of 1 is 9 divided by 1 gives me 2 feet per second. Okay, so I do it to the left, I do it to the right. I know that my instantaneous rate of change has to be between 2 and 3. And so what we do now is we say, okay, with things like tables, right now with this table, the way it's given, we don't have the ability to get any closer to 1. Right? On the graph, we could because we had more values and a little more flexibility, but we don't know anything about what's happening in between. And so in these scenarios, we have what's called a best guess. So the best guess for our instantaneous rate of change is going to be to average the left and the right together to see what's in the middle, right? So this is going to give me 2.5 feet per second. So this is my best guess for what the instantaneous rate of change is, given this table, given this information, since I can't make it any better, okay? So we have the left-hand approximation, we have a right-hand approximation, and we have our best guess, okay? But we know from the graph that if we were able to get closer to 1, right, information about what was happening closer to 1, that would make our interval smaller and more accurate than what we have here. So now let's imagine that we were able to do the same experiment, but we were able to measure what was happening every half a second, right? So the 0, the 1, the 2, those values are all the same. The difference is now we know what was happening at 0.5, 1.5, 2.5, and 3.5, the half-second intervals. So we're going to repeat the same thing, only now we're going to be using the closest data to 1, which is a little bit closer, right? So instead of 1 to 0, we're looking between 1 and 0.5. Okay, so we're going to do the same thing again. I want you to find the left-hand approximation for average rate of change, the right-hand approximation for average rate of change, and then your best guess based on averaging those two numbers together. And I want you to consider if the span between these is significantly smaller than 2 to 3, which is what our span was last time. Okay, so take 2 minutes, do the left and the right, think about what this means in context, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So let's check this one out and see what we learn about getting a little bit closer. So now, when we look at the left and the right, when we do the left, we're going to do f of 1 minus f of 0.5 divided by 1 minus 0.5. So here we have 9 minus 7.8 divided by 0.5. So be careful when you change the units that you remember what you're dividing by. It's really easy if you've been dividing by 1 a lot to then just divide by 1. But here we're dividing by 0.5 because the difference is 0.5. So when we calculate that, we are going to get 2.4 feet per second. Okay. When we do it on the right, we're doing f of 1.5 minus f of 1 divided by 1.5 minus 1. F of 1.5 is 10.1 minus f of 1 is 9 divided by 0.5. We get 2.2 feet per second. So before, our span was 2 to 3. Now our span is 2.2 to 2.4. So that is a much smaller span. So that's really good for us. Our approximation is getting significantly better. And so our best guess here is to average these two together, and we get 2.3 feet per second. Okay, so this best guess is better than the first best guess because our information is better. So before we were approximating 2.5, but we know now that the instantaneous rate of change can't be 2.5 because it has to be between 2.2 and 2.4. So we've updated it to a better best guess, I guess is the way we'll say it. Okay, so ultimately, the closer we can get to 1, the better our approximation is going to be for our best guess. And remember, the goal, right, is to get these two to be the same. So let's say that we had someone who has incredible equipment and is able to measure the height of this ball at 0.99 and 1.01, right? So within 1/100th of a second, which is like super incredible. They have the best equipment. So we have the height here. We again want to do the average rate of change to the left and to the right, see what shakes out. Okay, so you're going to do the same thing. Be extra careful with the decimals here. They're teeny tiny. So when you're plugging them in, just be careful. And let's see what shakes out when we're within 1/100th of a second. Okay, so I'll give you 2 more minutes and then we'll go through it together. All right. So you may have noticed something very interesting happens in this particular case. okay? So when we do f of 1 minus f of 0.99, we are doing 9 minus 8.976355, and then dividing by 0.01. When you plug that all into the calculator, you get 2.3645 feet per second. When you go ahead and do the right-hand average rate of change, we're doing 9.023645 minus 9 divided by 1.01 minus 1. And when you plug that in, you get 2.3645 feet per second, right? So this is what we are hoping will happen, that we get close enough that the average rate of change from the left is the same as the average rate of change from the right. And then we can say the instantaneous rate of change is 2.3645. Okay, it's no longer an approximation if you have the same value on the left and the right, right? We have found the actual instantaneous rate of change by getting close enough. So we are bringing in this idea of closeness again to say that if we get close enough, we can find the instantaneous rate of change, okay? So up here, approximation, down here, exact instantaneous rate of change. So when you can, you want to get as close as possible. As we know, it's not always up to us. Sometimes we are given the data and we just have to work with what we have, okay? So here's a few things that we sort of need to talk about in terms of terminology and notation. The important thing to remember about all of this is that what we are finding is the slope of the tangent line, okay? That is what is happening in the background with all of these calculations, is that there's some function, that function has a tangent line at that point, and what we are calculating or approximating is the slope of that tangent line, because that tells us how much the function is changing at a point. Now, we've been using the words instantaneous rate of change, but there's also some notation that we could use instead of the words. And so this is where things get a little weird. Okay. So the notation that goes with instantaneous rate of change starts like this, dy dx. So if we're talking about dy dx, we're talking about the rate of change at a particular point. So this will be included with some information about the point you're looking at, okay? This notation and wording, instantaneous rate of change, was introduced by a guy named Leibniz, Gottfried Leibniz, in the 1600s, okay? Now, at the same time, there was another guy inventing calculus, right? So they're both just sort of holed up, there's plagues, everybody's inside. Two different people invent calculus. Gottfried Leibniz, who says instantaneous rate of change and uses this notation. And also, at the same time, we have Newton, who is inventing calculus, but he is calling the same calculations, he is calling this the derivative. And he uses notation that looks like this, f prime of some number, okay? So Newton uses the word derivative in notation that looks like this, where a is the number that we are considering. So when we were doing this on the table before, Newton would have said we were looking for f prime of 1, okay? Now, unfortunately for us, this was so controversial and so evenly divided that nothing ever got settled, which means we use both sets of words and notations still today, right? So again, this was the late 1600s. Now we're in 2021. We still use both sets of notation, right? And they mean the same exact thing. They were just approaching it in different ways. And so since they developed them separately, they had different things they called them. And so we're stuck with both versions of this, right? So we're calculating the same thing, the slope of the tangent line, but we could call it the derivative. We could call it the instantaneous rate of change. We could use the notation dy dx, or we could use the notation f prime of a. That makes it a little confusing just because now we have all these things that mean the same thing. And the reason I bring this all up is because if you go into another class, there's no guarantee that they're going to use one over the other. So in physics, they often are going to use the Newton notation. So if you're in a physics class, you're likely to see the word derivative in the notation like this. In econ, it can go either way. In engineering, they tend to use this notation. So it really just depends on the context and the textbook. So I wanted to make sure that you've seen it both ways and that you know it's the same thing. Okay, so that's sort of the craziness that was calculus in the late 1600s. It was a wild time. They had really big hair. Okay, so now that we've talked about the notation, let's continue on with our calculation, which is the more important part of all of this. So we've been looking at approximating the instantaneous rate of change at a particular point. We were looking at 1 for all of these, but another strategy that we're going to employ a lot in this class is that we are going to be looking for the instantaneous rate of change for every point on a table so that we can get an approximation of this data of rate of change over time. Because our goal is going to be to come up with what's called a derivative function. So by taking the instantaneous rate of change at a lot of different points, we can put those points together to form its own function. So what we want to do is we want to find the instantaneous rate of change for every single point on this particular table. Okay, we've already done average rates of change on tables, so that's what we're going to be applying here to think about this. So as a reminder, when you're on an endpoint, you can't do the left and the right because there's no left for this case and there's no right for this case. So if we're approximating the derivative at 1, we would only use the point to the right. And when we approximate the derivative at 5, we only use the point to the left because there is no other point. However, for 2, 3, and 4, we have 2 ways to approach this. What we were doing today is we were finding the rate of change to the left, we were finding the rate of change to the right, and then we would average those 2 numbers together to get our best guess. Okay. The other way you can do this is you can take the point to the right and the left and do one average rate of change calculation. So what does that mean? If you want to approximate, right, the instantaneous rate of change at 2, you can take the points next to it and do f of 3 minus f of 1 over 3 minus 1, because it's going to do the left and the right and average them in a shorter calculation. It's up to you whether or not you want to do that, or if you want to do the left and the right and then average them. It's just a matter of preference. So you're going to approximate the instantaneous rate of change for 1, 2, 3, 4, and 5, and you're going to fill in this table. It'll be good practice for approximating these things. Again, we're using the average rates of change to do this. So I'm going to give you about 2.5 minutes, maybe 3, depending on how it's going, and then we'll go through it together and talk about what it all tells us. Okay, take about 30 more seconds. Okay, so again, when we're on the end point, we have to use the point right next to it because we don't have any other data to work with. So when we're approximating what's happening at 1, we're going to use the point next to it, which is 2. So f of 2 minus f of 1 over 2 minus 1 is going to give us 16 minus 7 divided by 1, which is going to be 9. Similarly, down here at 5, right, we're going to use the points 5 and 4 because that's the only point next to it. So f of 5 minus f of 4 over 5 minus 4, 79 minus 52 divided by 1, that's going to give me 27. Now, when we're in the middle, we do have a point to the left and the right, but as I mentioned, we could do the calculation by using the 2 points around it. This is the same as if you were to do the left and then the right and then average them together. It does it all in one calculation. So here, f of 3 is 31, f of 1 is 7, divided by 3 minus 1. 3 minus 1 is 2. So here, when we do this, we get 24 divided by 2, which is going to give us 12. Okay, so when we do f of 3, we're going to use f of 4 minus f of 2 divided by 4 minus 2. So f of 4 is 52. F of 2 is 16 divided by 2. It's going to give us 36 divided by 2, which is 18. And then finally, to do f of 4, we can do f of 5 minus f of 3 over 5 minus 3. When we do that, we're going to get 79 minus 31 divided by 5 minus 3, which is 2. Let's see, when we do that, we get 48 divided by 2, which gives me 24. So now I have an approximation of the instantaneous rate of change for this entire table. Now, we did this before with average rates of change to think about the concavity, but again, the instantaneous rate of change is a better approximation than the average rates of change. Even though we are using average rates of change, we're using them slightly differently than we were before. So this is a better approximation, and we can also use this to talk about the concavity the same way as we did with the average rates of change. So we said, if the first derivative is increasing, like it is here, that is going to make the function concave up. So the same analysis works, and this is even a little bit better than just doing an average rate of change between every 2 points down the table. Okay, so finding the instantaneous rate of change for every point on a table is something that we actually do a lot in this class because we end up analyzing what's happening here quite a bit. So this is something you want to get really comfortable doing, these calculations. And so this is how we set it up. This is how we do it. And we will do it quite a bit. Okay. So the next sort of example is meant to be a reminder about what the derivative is. And so just as a reminder, the derivative, or the instantaneous rate of change, is the slope of the tangent line, right? That's like the thing we always have to remember. So we have this graph below of f of x, and we're trying to figure out for each of these points, -2, -1, 0, 1, and 2, if the derivative is positive, negative, or 0. So remember, the derivative, or the instantaneous rate of change, is the slope of the tangent line. So we'll do the first one together. So f prime of -2 means that we're going to go to -2 on the graph. We're going to draw in a dot, and then we have to imagine what the tangent line is going to look like, right? If you have it printed out, you can try to sketch it. And once we have an idea of what it looks like, we're trying to figure out, does this have a positive slope, a negative slope, or a 0 slope? So if it goes down from left to right, the slope is negative. If it goes up from left to right, the slope is positive. If it's horizontal, then the slope is 0. So this one goes down from left to right. So we know that the derivative at -2 or the instantaneous rate of change at -2 has to be negative. Okay, so we want to do this for all of these points. I'll draw in where the points are on the graph, but you need to think about whether the derivative or instantaneous rate of change will be positive, negative, or 0. So 0 is here. 1 is here. And 2 is here. And this one was -1. Okay, so take a minute and a half, try to visualize that tangent line and determine if the slope of that line is positive, negative, or 0 for each of these points. Okay, so let's go ahead and sketch in these lines and see if you're able to envision them correctly. So here at -1, here's our point. If we're sketching in the tangent line, that's something like this. So it's going to be going up from left to right. So here, that's going to be positive. Right now, we're only interested in the sign. Later on in chapter 2, either Thursday of this week or next week, we'll be figuring out exactly what the value of that slope is. But for now, we just want to know if it's positive, negative, or 0. So at 0, we have this point here. If we draw on the tangent line, it looks like this. And so it's going to be horizontal. It's right on the axis. And so if it's horizontal, that's when we have a 0 slope. So then the next one we have f prime of 1. That's over here. So if we just sketch in a little tangent line here, we can see that's going down from left to right. So that one is negative. And then finally, the last one, we're sketching a tangent line. It's going to be going up from left to right. So therefore, the slope is positive. Okay, so there's going to be times when we need to just figure out if the derivative is positive, negative, or 0. There will be times when we need to actually approximate the equation of this line. We might need to approximate just the numerical slope of the line, but this is sort of our first step. Just is it positive, negative, or 0? We will develop how to determine the actual numerical value of the slope, and then we'll also be able to figure out the equation of the tangent line eventually. Okay, so that's just sort of reconnecting to the fact that the derivative or the instantaneous rate of change is the slope of the tangent line. Okay, the next problem is going to help us understand the different ways that we might ask you to do this on a quiz. So we're going to do this in general, and then I'm going to talk about all the variations of how we might ask this so that you know all the different terminology and ways that we might study this. Okay, so the question itself is approximate the instantaneous rate of change for f of x equals 4x squared at x equals 3, which is the same thing as asking for f prime of 3, right? These both represent the derivative or the instantaneous rate of change. So what we know till this point is that we want to get close to 3, right? That's always our goal, get as close as we can. Average rate of change on the left, average rate of change on the right. So how do we set this up? We need to set up our own table, okay? So we need to pick values close to 3 to put into our table. That is probably not enough space, but that's okay. So 3 is the one in the middle. I want to go the same amount to the left as I do to the right. So again, this idea of closeness, I want to pick a value really close to 3 on the left and a value really close to 3 on the right. Once you do that, once you've picked your values, you're going to plug them into the function to get the corresponding f of x value or the y value, okay? So if you were to plug in 3 into this function, you get 36. We also have to plug in whatever values we pick on the left and the right, okay? Then once you have those values, we're doing average rates of change to the left and average rates of change to the right. Okay, I'm trying to be a little bit vague about picking the values because I want to make sure that you're remembering this idea of closeness, but that's the process. So pick a value to the left and the right, same distance away on either side, close to 3, find the corresponding y values, then do the average rate of change to the left and the average rate of change to the right. Once you have those, you can average those two numbers to get your best guess for the instantaneous rate of change. Okay, so I'm going to give you about 2 to 3 minutes to get that set up, try it out, and then we'll talk through it together. Okay, take about 30 more seconds. Okay, so again, we want to make sure we understand this idea of closeness. And there's a couple different ways to do it that are totally fine. I will tell you that I picked 2.99 and 3.01. But if you picked 2.9 and 3.1, that's fine. If you picked 2.999 and 3.001, that's good too, right? But we want to be within at least 1/10 of 3. And so for me, I just made this box too small, so just ignore this line down the middle. What I did was I picked a delta x that equals 0.01. Okay, and I'm pointing out this terminology, and we'll talk about that after we finish solving the problem, but that's how close I chose to be, is 0.01 away on either side. So when I plug in 2.99 into my function, I get 35.7604. When I plug in 3.01, I get 36.2402. Obviously, if you pick slightly different numbers, your decimals are going to be slightly different than mine. That's totally fine. We should still end up approximately with the same instantaneous rate of change. So when I do my instantaneous or my average rate of change on the left, I'm going to get 23.96. And when I do it on the right, I get 24.02. okay? Which means that when I average those together, my best guess is going to be 23.99. Okay, so I averaged my left and my right, and that gives me 23.99. Now, there's three different calculations that happened here, okay? There's the left-hand approximation, which is when I used the average rate of change to the left. There's the right-hand approximation, and then there's the best guess. When we ask you to do these types of things on a quiz, we obviously can't just let you pick whatever you want because it's going to vary slightly depending on what you pick. So typically what's going to happen is that you will be given the delta x. So if you are given 0.1, then you would use 2.9 and 3.1. You're varying by 0.1. If you're given delta x is 0.01, that means you're varying by 1/100th. Okay, so if you see this like triangle and then either x or t, depending on your variable, that's telling you how to set up your approximation. Okay, in addition to the delta x, there's three different things we can ask you for. We could ask you for the left-hand approximation only. So we could say approximate the instantaneous rate of change of f of x, blah, 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 using delta x equals 0.01 to the left, or using a left-hand approximation, which means that this is the number we are looking for. Okay. If we were to say using a right-hand approximation, then that is the number we are looking for. If left or right is not specified, the default is to average them. It's the best guess. Okay, so there's a lot of different ways to ask this question, but a lot of things will be specified for you so that you get the number we are looking for on the quiz, since it's multiple choice. Okay, I'm going to caution you, if you have taken calculus before, you cannot just take the derivative using derivative techniques and plug in 3 to get a left-hand approximation with 0.1, because this is going to be the right answer, 23.96. Okay, so if you've not taken calculus before, then that probably doesn't make sense to you, and it doesn't need to, because that means you'll do it this way and you will get it right. Okay, so there's two more problems. I really want to make sure we do the last problem because it's slightly different. So I'm just going to give you an outline of problem 4, because problem 4 is almost the same as problem 3. So for problem 4, we have a different function that's an exponential function instead of a polynomial. Okay, time is in years since 2010, and we want to know what's happening in 2012. So for this problem, we want to know the instantaneous rate of change at time equals 2. So we're just going to set up our table. We're going to stick 2 in the middle. We're going to pick something to the left. We're going to pick something close to the right. We're going to plug those values in and then do the average rate of change to the left and the right, just like we did here. Okay, so when you do that at home, you should get an answer of 8.43. Okay, so try that one at home, but that one's pretty much the same as this one. And so we want to jump to the one that we haven't seen yet here. So here we have a function f of x, and we have some information about this function. We know that f of 4 equals 25, so that's a functional value. And we know that f prime of 4, so the instantaneous rate of change or the derivative at 4, is 1.5. We want to use this information to find the values, or for the coordinates, for A, B, and C. So our goal is to have the coordinates for all 3 of these dots. So C is on this line, B is on this tangent line, A is on the tangent line and the function. Okay, so I want you to think about how we might be able to use what we've learned about derivatives and instantaneous rates of change, along with what we know about functions, to figure out the coordinates of these points. Okay, it's a little bit tricky, but I'm going to give you 2.5 minutes. Try it out, see what you can come up with, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so let's see what we know, what we have to figure out, and how we put it all together. So the first thing that we need to do is understand what this is telling us, that f of 4 equals 25. So f of 4 equals 25, this is a functional value that says when x equals 4, y equals 25. So you notice that we don't actually have the axis here, right, like we normally would. So we just have to kind of imagine what that axis would look like. So what this is telling us is the coordinates for the point A. When x equals 4, y equals 25. That's what this piece of information is right here. It's the literal coordinates of the first thing we're looking for. Now, we also know that the rate of change at 4 is 1.5. So remember, the derivative or the instantaneous rate of change is the slope of the tangent line. So this is the tangent line that's drawn in where all these points live, and it's touching at 4, which means that what this is telling us is the slope of this line, oops, which is positive 1.5. That should be a positive one. Okay, so we have the slope of the line and we have a point that's on the line. So if you have the slope of a line and a point on the line, you can get the equation of the line. So usually we have y equals mx plus b. So my m here is 1.5. And I can solve for b by using this point. So 25 equals 1.5 times 4 plus b. Notice that the plus b here is part of the line equation. It's different than the point b that's here, right? These are different b's. So 1.5 times 4 is 6. So we subtract 6 from both sides, and we get b equals 19. So the equation of my line is y equals 1.5x plus 19. And that's the equation of this tangent line. So now, if I want to find the coordinates for point C, I can take this 3.9 and plug it into this equation to get the corresponding y value, right? So for point C, I have 1.5 times 3.9 plus 19. If I crunch that number, I get 24.85, which means the coordinates for point C are 3.9, comma, 24.85. Okay. Similarly, to get the coordinates for B, this one in blue, B happens when x equals 4.2. So I need to plug a 4.2 into my function. So 1.5 times 4.2 plus 19. If I crunch that number, I get 25.3. So that's the y value here. So that means the point here is 4.2, comma, 25.3. Okay, but the reason I'm able to get these points is because I'm able to find the equation of the line, which I'm able to do because I have information about a point and a slope of the line. So the critical piece of information here is about the instantaneous rate of change, and we're using the fact that the derivative or the instantaneous rate of change is the slope of the tangent line. Okay, so that's how we put that all together to find those coordinates. I do think you have a problem very similar to this on the homework. So you may want to start this in your notebook so you can refer back to it. Have a great rest of your day, and I will see you all on Thursday.